Hi guys, welcome to our channel of Sciences and Mathematics. Our topic of discussion for today is going to be the vector of a cross product. And we're going to see that this vector of cross product, of course, displays as a specific characteristic that is going to be applied in some of the topics that we have already discussed, maybe in mathematics and physics. So in this case, I would like us to have a keen interest on this specific behavior so that whenever we come across it, we're able to apply it appropriately as already been discussed in some of our videos. So this, without further ado, I'd like to welcome us to the discussion. So in that case, as I've said, we're going to look at the vector of cross product. And this is going to be just a build-up or maybe a complementary, of course, concept that is going to add up on the concept that we have discussed about the vectors, that is a cross and dot product. But specifically, this is going to be biased around the concept of a cross product. Now, the vector or the cross product of two vectors, let's just give a hypothetical vectors for our case for 2 and b in a two-dimensional space. Is given as a cross b equals a b, the sign of theta, and then this particular set, just a part of that definition implies the direction of that specific vector, and we're going to define those specific terms. So for that case, this is the definition that we're going to give for the vector of a cross product, where A implies basically the norm. We say this one implies the length of A, vector A, whereby B implies the length of vector B, and theta is the angle between A and B, and N, that one is going to represent the unity vector perpendicular and just use this symbol, that is, it implies perpendicular to the plane of A and B. Or perhaps just use the specific ones that we have used, the plane of A and B. So to illustrate that one, just have to draw this specific coordinate, whereby we have two vectors AB, and then this is theta, the angle between them. Now, this specific point, we have a unity vector, which we are going now to represent by M in that specific direction. So therefore, the cross product of vector A and B in the positive direction is going to be represented as A cross B. But now that I've also indicated on the opposite direction, this one can be represented as B cross A, or just being given as negative A cross B. So therefore, basically from this definition, this is how we try to define the concept of those specific vectors. Now, whenever I'm just trying to use maybe the small caps letters for that case, it implies the specific letters of the alphabet, maybe in the capital letters or the small, insofar as this illustration is concerned. So for that case, I hope that is going to be used as such as we go ahead. So the definition of a cross product gives us some of the behavior we are going to see, which is reflected in some physical quantities that I've already mentioned. Now, basically, this implies the application of this specific formula for the vector of cross product. And as I said in one of our videos, we're going to find this specific behavior of the cross product, which is being displayed in trying to find or calculate the aspect of torque in physics. And then we are going to see it being applied, of course, trying to find the angular momentum, this in circular motion, and then we are going to see it being applied in magnitude, finding the magnitude of a force, and perhaps in the concept of charged particles. And this is going to entail specifically to the concept of electricity when we are trying to describe maybe the motion of some of the aspects we're going to discuss under electricity. This formula is going to be applicable in that. And in this case, of course, this direction that I have indicated M here gives us a particular convention that we normally use, which is referred to as the right hand rule. So the combination of behavior of those specific vectors or the movement of that specific vector, the unit vector, which is represented as n, or as sometimes we're going to represent it using an arrow like that. So this one gives a specific characteristic which is going to be used in some of these fields, and this particular convention is known as the right hand rule. Right hand rule, in a sense that whenever we try to encircle the fingers of the right hand rule, the thumb is going to face, of course, in a specific direction, and the direction of motion, or maybe the direction of rotation of the fingers, is going to give us an aspect of this specific rule that we are talking about. So that when we talk about it, whenever we are trying to talk about the right hand rule, which I've said is going to be applicable in this specific field. So one of the essential part, or maybe the application of these vectors of cross product, is trying to find quantities of the direction of those specific aspects I've mentioned on the board. So for the order of cross product of vectors, in this case, we're going to see that it's non-commutative, in a way that if I have vector A and B, then this is one of the properties that we are going to experience, whereby A cross B is not going to behave the same as B cross A. But we are going to see that B cross A is going to behave as negative A cross B, as we have already illustrated in one of this demonstration of this figure that we had indicated, whereby we say B cross A is equals negative A cross B. So therefore, this is the specific rule of non-commutative property of this vector of cross product. So therefore, this is one of the characteristics that we will have to check on whenever we are trying to maybe deal with these vectors. But in this case, we are going to see another property whereby the vector product has got a property that we call a distributive property, whereby if I have maybe three vectors, that is A, B, and C. Now for B and C represented as such, then we are going to have AB plus AC, just like that. So this one is called a distributive property, in that this factor of A has been distributed amongst those properties which are vectors which have been given in the product brackets, of course. So for this concept of a cross product to apply in this particular phenomenon that we have mentioned on the board, to a unity vector, or the unity vector that we had mentioned for the ij and the k components, just indicated it, so just do like that. So for it, this property that we have mentioned to apply in the unit vectors for I, j, and k components that we have mentioned of the coordinate system must be right-handed. Right-handed in the sense that we're going to see that there are some specific behavior of these vectors that we're going to use in order to give a general definition for the right-handed system for these vectors in three-dimensional space. So maybe I can just mention a few, or just generally mention these are some of these properties, so that in case we come across them, we will be able to determine whether this particular vector of cross product is applicable or not. So just write this coordinate system that I've mentioned. This is for x, y, and z. And then for a right-handed system, to apply, we're going to see that the cross product of these respective components, j cross j, k cross k, is going to be 0. So therefore, from this case, of course, as we defined this, we're going to see that these components are going to have a specific behavior, in a sense that we're going to see that property being applied. But for the I, k, we're going to see that this also are going to hold. J, I is going to give us negative k. This basically is the opposite of this first application. And then we're going to have k cross I is equals j. Then therefore, also we're going to have I cross k with respect to the one that we have mentioned. It's going to be negative j. And then j cross k is going to be I. And lastly, we're going to have k cross j. It's going to give us negative. And so this specifically is the interchange of those specific ones, and they're going to give us an opposite direction for that. So the general expression for the vector product for a vector C, which is a product of A and B, is going to be represented in this general way. So we said for us to represent the vectors A and B, we had mentioned about the the specific components for vector A, and said that this is made up of those three components of that specific vector. And respectively for B, there are components for B. This is for J specific element, and then plus B, Z, K respectively. So in this case, we're going to do a cross of those two specific vectors, and they're going to give us a component for vector C in the X, Y, and Z direction, whereby we're going to see that we can as well find the components of this specific cross product by trying to find the determinant of A and B, which is a most convenient way for us for now, because of space, because I know we're going to deal with the vector for I, J, K, X, Y, Z for that C. We can just generally illustrate that one by using the strategy or the concept of a determinant by writing those specific components for I, X. This is AY, AZ, BX, BY, BZ, whereby the first product for the I component is going to give us a positive and then minus. So we just specifically use this order. Whichever product is that is going to be given by the ith component is going to be preceded by a negative sign. So the first one is going to be positive, whereby this is AYBZ minus AZBY, a positive. So if you do the second one, which is a cross between AXBZ minus AZBX, this is specifically is going to be preceded by a negative sign. So whatever component that we find in the second part of this particular case of finding trying to find the determinant, it's going to be second negative, as we always do in that case. So for this one, it's going to be one of the strategies in which we're going to use this particular concept that we have discussed about the vector of a cross product. Whenever we are trying to apply it in these specific areas that we have talked about in finding angular momentum torque, trying to find some of the resultant forces that are being experienced in charged particles, and even in maybe magnetic fields and force. So for that case, basically try to remember about the concept of the formula that we have discussed about. And this is the cross product of two vectors, AB, which is the magnitude of A, the magnitude of B, the sine of theta, and then in the specific direction, which is normal to the plane of the vectors for A and B. So therefore we have done that one using an illustration, and therefore since we have just used similar examples to try and find out the product of vectors using sample questions, we're not going to use a sample question in this case. So presuming that we have already understood the concept on how we come across that specific formula, therefore I'm going to just stop there, guys. I hope that whenever we come across this concept of vectors of cross products in physics, maybe under the concept of torque or angular momentum and other areas, of course we're going to apply it as we have discussed. So that for that case, thank you and bye. God bless.